Today we're going to talk about how to smooth electrocardiogram signals. That is the electricity of the heart. In a previous video, we graphed the EKG data, but in order to make it useful, we have to smooth it out. If you remember from the last video, we mentioned how much noise there is going on between these big peaks. These big peaks are the R waves. In our previous graphing video, we talked a bit about what EKGs are supposed to look like. Here is a super smoothed out version of what one heartbeat looks like on an EKG, but from our graph in the last video, it doesn't quite look like that. We have the big spike in the middle, which is the R wave, but all the stuff in the middle is kind of jagged and it's tough to read. So what we have to do now is smooth it out. We're going to do this in two main ways. The first is we're going to feed our data into a library or add-on for Python called Neurokit. And then separate from that, we're going to use some common filters in digital signal processing, such as median filters, the Savitzky-Golay filter, and the Butterworth filter. Each has their own pros and cons for filtering certain types of signals, so we'll show you how each performs on EKGs in particular. This tutorial assumes that you're pretty new to Python. Maybe some terms or things will be kind of new to you, but we'll try to explain as we go along so that you can still get the gist of how you can do this yourself. We'll also have code that you can copy yourself and play around with after so that you can continue learning. What we're going to use to write our Python code is a website called Kaggle. Kaggle allows you to create a free account, log in, and immediately start coding in Python or R. You don't have to download or install anything onto your own computer. All you need to do is come to the website, pick any one of their thousands of free datasets, and then create a notebook on that dataset, and in the notebook will be your code that analyzes the data. For this tutorial, we've uploaded a dataset of 18 EKGs, each 24 hours long. So if you want to follow along with us, all you have to do is come to this data page. The link will be in the description. Go to the top right options, click New Notebook, and then Kaggle will make you a new place to write Python code, and the dataset that we just showed you will be automatically loaded. So a quick rundown on Kaggle notebooks. If you're not new to Kaggle, you can probably skip the next 60 seconds of explanation. When you make a Kaggle notebook, it will give you some placeholder code, which you can see in this gray box here in the middle. This is just loading some add-ons or libraries that typically come with Python and that people typically use when they're doing data science. We're only going to use a couple of these for now, but let's just delete all of this and then let's name our notebook Smoothing Electrocardiogram Signals in Python. Oh, there's not enough room. Well, there's a character limit on the titles. Okay, let's talk about why we need to smooth these signals. I mean, surely we can just open the EKG and then feed it into a machine learning algorithm, and then the algorithm can find all the patterns and we can figure out what's wrong with the heart, right? Well, machine learning leaves about 100 years of cardiology knowledge on the table. It may seem like when you look at an EKG that it's just a bunch of squiggly lines, but there's actually so much information in these squiggly lines. Underneath all of this noise are actually waves that signify steps of the heartbeat. We touched a little bit on this in the graphing video, but if anything is out of order, or it's beating too weakly or too strongly, or things are happening too quickly or too slowly, that signifies that something's wrong with the heart. If you're looking at an EKG, if a certain wave is too tall or too short, or it's too close to another wave or too far away, that means that the timing of the heartbeat is off, or it's beating too strongly or not well enough, which means that blood isn't moving from the heart to the rest of your body very well. Notice the difference between these smoothed out drawings of EKGs, where the waves are very clear, and then take a look at the one that we graphed from the graphing video. It is almost impossible to eyeball what these waves are. If you've looked at enough EKGs, maybe you can tell that this is a P wave and also this is a P wave. The big spikes are very clearly R waves, but all this jagged stuff in the middle will just confuse you, or confuse whatever algorithm that you push the data into. Now, there are algorithms where you don't need to clean things up. You can shove all of the noisy data right into it and it'll be fine. So instead of the EKG looking like big R waves and then some jagged spikes in the middle, at the end we'll see some clear P waves and T waves on either side of the R waves. And then we'll actually be able to learn how to measure EKGs and how to measure the waves and determine, is this a good heartbeat, is this a healthy heartbeat, or is this an arrhythmia, a bad heartbeat? And what type of arrhythmia is it? In fact, there are a few hundred different types of arrhythmias that you could possibly see. If you want to learn more about these, check out this website, Life in the Fast Lane. This is a popular EKG site for nurses, doctors, paramedics, and you can start to learn what EKGs look like when things are going wrong. Alright, let's get started on coding. So go over to the normal sinus rhythm database on Kaggle. It should be linked in the description. Go to the main page, going to go to the top right, click the 3 dots, and then in the drop-down, click New Notebook. We already have a blank notebook here called Smoothing Electrocardiogram Signals. And because Python isn't that good at analyzing signals like these with just its built-in library, we have to bring in an add-on. The one we're going to use is called Neurokit. So this first part is going to be a little confusing. If you're new to Python, kind of just ignore this and just copy it as is. What we're going to do is use a little part of Python called pip that handles all of these libraries. And we're going to tell pip, hey, we want to install Neurokit. The official name for this for installation is Neurokit 2. Again, confusing, not super important. If you're new to Python, ignore me for now. Just write out pip install Neurokit 2. And then we added -- quiet just so that this Kaggle notebook doesn't print a bunch of crap as it's installing Neurokit. So what we're going to do is run this cell. You can either press the triangle to the left of the cell, or you can press Shift Return or Shift Enter on your keyboard. And then what you'll see is the notebook will actually start running. You'll see a yellow dot up here at the top of the notebook, and then to the left of the cell will be this little loading icon. This Python notebook was actually just sitting and sleeping before we ran our first cell, so now it actually has to start up and start installing stuff. Okay, so pip has installed the library that we wanted to use, Neurokit 2, and now we're going to import Neurokit. It seems a little weird that we have to first install something and then import it. This seems a little redundant, but we'll explain this in future videos. Alright, so we have Neurokit installed and imported. Now there's a second library for Python that we're going to use to open our data. Python does an okay job at opening files, but we're going to use a special library that's really good at opening CSV files. If you check out the data info window over here on the right, you'll see that in the dataset that we based this notebook off of, all of the files are either CSV files or what are called JSON files. These files are just two different ways to hold data. You can think of CSVs as like a super simplified Excel spreadsheet. Doesn't have any of the fancy formatting, just has the headers, the rows, and the columns. By putting data in this format, it makes it super easy to load into Python and start analyzing. So this CSV opening library that we're going to use is called Pandas, like the bear. To include it in our code, all we need to write is import pandas. The last library that we need to load is the one for graphing. This one is called Matplotlib. In fact, we're going to load just a subset of this library. We're going to type import matplotlib, and then we're going to write .pyplot. Now before we run this cell of code, this little gray box with just the 2 lines with pandas and matplotlib, we're going to rename how Python loads these libraries. So if you've ever looked at data science tutorials before, you may have seen people tend to rename pandas as PD, and then maybe you've also seen they tend to rename Matplotlib as PLT. What this will do is allow us to, in our later code below, whenever we want to use a pandas thing, we only have to write PD dot whatever to call a pandas function or to use pandas. Likewise with PLT, when we want to create a graph, we can just do PLT dot and then whatever function we want to use for graphing. For example, if we wanted to add a title to our graph, which we'll go over again later, we would just write PLT dot title, and then we would write whatever the title is. We'll get into the specifics later, but that's just a preview of how we'll reuse the renamed libraries. Okay, we're going to run that by pressing Shift Return. Again, you can also hit this little run triangle, Shift Return. Okay, so now these 2 libraries are imported. We have all 3 that we need, Neurokit, Pandas, and Matplotlib. Now we need to open the data. We need to open the CSV of actual EKG stuff. We're going to use a function called readCSV, And to use that, the bulk of what we need to write is pd.readCSV. And then we're going to give the readCSV function the exact name of our CSV file. So to get the name of our CSV file, we're going to go over here to the right, hover over the file we want to open, and then this copy file path icon will pop up on the far right. Click copy, and then what we're going to do is assign this file path. We're going to assign that to a variable called file path. So now file path is the actual file path. We could name this whatever we wanted to. File path 123, doesn't matter. We could name it ABC, but we'll call it file path so that it's readable. So now Python knows that the path to our CSV file is this Kaggle/input/datasets blah 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 .csv. And we're going to give that variable to the readCSV function. And then Pandas will be able to open our EKG file. To save the output of the readCSV function, we need to assign that to a variable. So let's call it EKG. We'll write EKG equals pd.readCSV parentheses file path. Let's run that cell by pressing the triangle. This will take about 15 seconds because these EKGs are 500 megabytes in size. They hold 24 hours of heart data. Okay, our EKG is loaded. All we have to do to see what's actually in it is type EKG and run that cell. I'll press Shift Return to run it, and Pandas will give us a preview of our data. Like we saw in our graphing video, this EKG is 11 million rows of data. Now for the columns, we have timestamps of when the actual heart data was recorded, and 2 voltage channels. This is the actual data that we're going to graph and smooth. You can ignore these columns on the right for now. Alright, let's run one of the EKG channels through Neurokit in order to smooth it. Neurokit is pretty cool. It provides a function called ECG process that analyzes an EKG signal all in one go. Part of that is that it also smooths the EKG. So we're going to feed our data into that function and then just grab the smoothed part and graph it. So let's grab voltage channel 1 and we'll assign it to a new variable. Let's call it channel 1. Channel 1 equals EKG brackets, and then in double quotes or single quotes, whatever you want to do, doesn't matter, voltage channel 1 MV, all with underscores. So we're going to run that, and then just for sanity, we're going to print out what channel 1 is. So we'll run that cell. And there are all 11 million rows of our EKG voltage data from channel 1. Now let's feed this into the ECG process function. To use the ECG process function, we need to write neurokit2 dot ECG process. And then in these parentheses, we're going to tell it what data we want it to process. We need 2 things. We need first the data itself, which will be channel 1. And then we need to tell it what the sampling rate of the data is. How many samples per second was the data taken at? We can find this out by opening this EKG's accompanying metadata file, which we uploaded as JSON. So if you go over to the data, find the metadata file for this corresponding EKG. Ours is 16265 metadata.json. If we click it, Kaggle will open it so that we can preview it. So you see this little window on the bottom. We can see some metadata about this person, like the comments say, hey, 32M, this is a 32-year-old male. And boom, here is the sample rate. It says it was taken at 128 hertz, or samples per second. Let's X out of that. So now, what we need to give to ECG process is the EKG data that we want it to actually process, channel 1. And then the sampling rate, sampling underscore rate, will equal 128. But of course we want to save the output of this function. We want the processed EKG and all of its accompanying data afterwards. So let's assign this to, let's call it processed EKG. And just so you know, ECG and EKG mean the same thing. EKG is the more popular acronym. It comes from the German spelling of electrocardiogram, which has a K, but ECG is equally as acceptable. I personally like to say EKG because when I'm working in the ER and I yell EKG, it's very clear what it means. ECG is a little bit easier to mishear. Anyway, let's run this. I'll press Shift Return to run that cell of code. And it's going to take quite a bit to process because this is 24 hours of EKG data. If you had like a minute of EKG data and fed that into Neurokit, it would only take like a minute or two to analyze, but this is going to take a while. Actually, you know what? Let's reduce the data just for illustrative purposes. Let's add a new cell of code above our ECG process function, and we're going to pare down the channel 1 data. So we'll do channel 1 reduced. We can call it, again, whatever we want, but we'll do channel 1 reduced equals. If you remember from the graphing video, to get just a certain number of data points, we can use bracket notation with a colon. So let's say we want just the first 1,000 data points. There are 11.7 million, so we have quite a bit to choose from. So to get just the first 1,000 data points, we're going to do channel 1 brackets 0 colon 1,000. This will make the ECG process function go a little bit faster. Okay, so let's run that. Click run. And then let's print channel 1 reduced just as a sanity check. Run that. Okay, now we only have items 0 to 999, which is basically 0 to 1,000. If we wanted the actual 0 to 1,000, we would write 0 to 1001. This is just the way that data gets indexed in most programming languages. Rerun channel 1 underscore reduced. Now we have the actual first 1,000 data points. Alright, let's rerun the ECG process function on the reduced data set. So we'll change this name to channel 1 underscore reduced. Alright, go ahead and rerun that cell. Okay, let's see what Neurokit gave us. We'll write processed underscore EKG, run that, print it out. Alright, we have a bunch of post-processed data. What we're looking at is a bunch of rows and columns that are printed, kind of smushed together. What Neurokit gives us back is largely two things. The first is a new data frame, and by data frame I mean spreadsheet-like variable with rows and columns and header names. It gives us that with the original EKG data, ECG raw, and then the next column to the right is the cleaned ECG or EKG. That's the smooth signal. We're going to show you how to grab that in a sec. And then past this data frame, all these columns, blah, 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 starting with these curly brackets, is actually the metadata. This actually contains the indices, or coordinates, so to speak, of the peaks of the EKG. That's these P waves, Q waves, R waves, S and T waves. We're going to use that in a future video to start measuring the EKG and start analyzing healthy and unhealthy heartbeats. Just as a preview, here's one item called ECG R peaks, and here is on the x-axis the coordinate or index of each R peak. There's also, it found the P wave peaks, the onset of the P waves, that's also important to assessing heart health, Q waves, S, T waves, etc. Okay, but back to what we really want to see for the smoothing part. To get just this first data frame, we're gonna use indexing again with brackets and say, hey, I just want to see the first part of this EKG result. That's going to give us just this data frame. It's not obvious, but the processed EKG variable holds two major things. The first thing at index 0 is this first data frame that you see with all the columns. And the second part is all this metadata with the curly brackets. If we wanted to get the second part, we would write 1, because it's the second item is item 1. This data frame is item 0. So let's just say, hey, I just want the first part of processed EKG. We'll run that, and it shows us just that data frame that we saw, but formatted a little more nicely. So again, we have our original EKG, channel 1 on the left, ECG raw, and then the smoothed one is under the column ECG underscore clean. We'll ignore the rest of this data for now. Alright, let's graph these two columns separately, the raw data and then the smoothed data. If you remember from the graphing video, this isn't too hard to do thanks to how well Pandas and Matplotlib work together. So what we're going to do is, let's reassign this. I'm going to say EKG underscore DF, or data frame, EKG underscore DF equals processed EKG item 0 in brackets. We'll run that, and now we have the data frame by itself. So we don't have to rewrite processed EKG brackets. Alright, now EKG DF, again, just to get the raw column, just use brackets again, ECG underscore raw. We'll run that cell just to print it out and show you what we got. 1,000 data points of voltage data of the raw EKG, and then we could do the same with ECG underscore clean. Preview that data, rerun that cell. All right, everything looks right. Okay. Now to graph this, again, write basically the same thing. EKG underscore DF, and then in brackets, ECG raw, dot plot with parentheses. And we're going to run that. And there we go. We have about 13 heartbeats, or exactly 13 heartbeats. But again, you see there's so much noise. Look at all those jagged edges. It's almost not readable. How do you know what's a P or a T wave, especially if you're new to looking at EKGs? It's tough to tell. Let's see how well the smoothing algorithm from Neurokit did. We're going to write almost the same thing. We're going to change the column name to clean and write dot plot parentheses and then run that cell and see how it did. Okay, that's a little smoother. Not as jagged in the middle. The waves are a little bit easier to make out. And we're going to zoom in on this just so I can illustrate to you better. Let's get just the first 100 data points. I used bracket notation again to say, hey, just want item 0 to item 100. And I just want to plot that from the clean EKG column. Replot. Okay, look how smooth that is. Not as jagged. Let's get 2 heartbeats. 2 to 3. Change that to 200. Okay, we got 2 heartbeats. And yeah, we can almost start to make out what the actual waves are. If you see to the left of the big spike R wave, it looks like there's a P wave. And to the R wave that's on the left, it looks like there's a P wave to the left of that too. And then look, we can see, instead of there just being a bunch of noise, we can see what looks like a Q wave. To show you guys again what we're looking for, we got the big R wave, and then 2 little to medium-ish bumps on the left and right. Those are the P and T waves. And then often you'll see these little down spikes called Q and S waves. You won't always be able to see noticeable Q and S waves on EKGs, but just know that they're there. All right, that is our smoothed EKG. Let's go ahead and add a title. Just for documentation purposes, we're going to say smoothed EKG and put in parentheses Neurokit 2. Just to differentiate our future graphs from when we smoothed with Butterworth filters, Savitzky-Golay, and median filters. So let's run that, and boom, there's our title, Smoothed EKG with Neurokit 2. Just to illustrate, I'm going to copy and paste this and run it on the raw column, just to show you guys the difference. Raw EKG, change the title. Okay, we're going to rerun that on the raw column. And you see how the jagged edges are still there. And there is the smoothed EKG. Okay, so that was smoothing with Neurokit 2's ECG process function. Let's show you how to do it without Neurokit. If we don't have a fancy library that does everything we want, how do we kind of do it by rote? Now we're not going to rewrite a filter function from scratch, but we're going to use something that's a little lower level. We're going to use a library called SciPy. SciPy is one of the go-to libraries in Python for doing digital signal processing. If you really want to get into the weeds of analyzing biosignals like EEGs, EKGs, EMGs, SciPy is great. It's good for filtering, you have access to Fourier, wavelet transforms, all sorts of stuff. So from SciPy, we're going to use the Butterworth, median, and Savitzky-Golay filters. And just like Neurokit, it'll only take like 1 or 2 lines to filter and print out the results. It's actually not that complicated. Alright, the first filter we're going to try with SciPy is the median filter. Make a little header just to separate. What we just did is write some markdown or non-code stuff just for documentation. Now going back to the top of the notebook, we did not import SciPy. So if we want to use it, let's go ahead and add a line to this little import cell. We're going to write import SciPy, and then we're going to rerun this cell, press the little run triangle, and now SciPy is imported. Okay. Alright, let's write down what we're going to do. We're going to start with a median filter, which you're going to see is maybe the least successful filter, and then we're going to show you some better filters like Savitzky-Golay and Butterworth. So how do we find this median filter function? How do we call it? Well, if you go to the SciPy documentation, you can see a list of all the functions that they have. We'll go to the reference guide. This shows us all the libraries and their functions. Let's see, we'll go to SciPy.signal, just because I happen to know that the median filter function lives under this library. And under the filtering section, Here we have perform a median filter on an array. There it is, medfilt. Alright, so to use the median filter, the bulk of what we have to write is SciPy dot signal, because it's a sub-library, dot medfilt, and that was the name that we got from the documentation. And then all we have to do is give it the EKG data that we want it to filter. Alright, let's grab the raw data again, just the first 1,000 data points. And we'll put that in the parentheses of the function. Again, because we want to save the output, let's assign it to a variable called median filtered EKG, put an equal sign, and then let's run that. And let's see what the output is. Median filtered EKG, run that cell, print it out. Okay, now what we have is an array of voltage data after the median filter. And then to plot it, all we have to do is use Matplotlib's plot function and give it as an argument. And when I say argument, I mean thing that we put in the parentheses of a function. Like if I wanted to use the print function to write something to the screen, the argument would be the sentence that I wanted to print. Or a number. That's the argument. So, in the plt.plot function, I will give the filtered EKG as an argument, and then just run that cell and see what the output is. And if you can kind of eyeball it, you see a slightly smoothed EKG. It's not amazing, but it's not as jagged as the initial EKG before filtering. Little more jagged up there. And just to illustrate how well it did, let's zoom in on that even further. So we can take this same plot function, let's say, from that, we can say, what do we have? We have 1,000 data points. It looks like a heartbeat happens about once every 100-ish data points. So let's just get the first 200 data points and plot just those. And maybe we can zoom in a bit on the filtered waves. All right. So it filtered it pretty well, but not as well as Neurokit, if I'm being real. Let's go back to the Neurokit one. Neurokit looks a little smoother. There's still some jagged edges, like you can see around data point 20-ish. There's this little blip. We still have little blips and boops and jagged parts after the median filter. So it did okay. It's still better than the raw EKG, but it's not the best we can do. Next, we're going to try a Savitzky-Golay filter. This filter is a little more dynamic, whereas a median filter just looks at its neighbors and uses the median of that value. A Savitzky-Golay filter uses polynomial smoothing. You know how if you do like a polynomial regression or you try to fit a curvy line to a scatter plot of data, you can think of polynomial smoothing as like a miniature version of that at each data point. It tries to fit a curve as it traverses the data from left to right. The name of the function that we're going to use is Savitzky-Golay filter. You can see this in the SciPy documentation, same page as last time. Scroll under the signal processing SciPy.signal page, and under the filtering section, you can see documentation for Savitzky-Golay filter. And we're going to give it a couple of arguments to say, here's how much data to consider, the window length, and the type of polynomial that we want it to use. So the function that we're going to use is SciPy.signal.Savitzky-Golay_filter. This is the base function. Now the arguments we need to give it are three things: the data we want it to filter, the window length, basically the neighbors of data that we want to consider for smoothing a single point, and then the polynomial order. This is just a number that says, hey, I want this to be a squared polynomial or a cubic polynomial, so a 2 or a 3. It'll make more sense in a second. So to make the Savitzky-Golay filter, we're going to give it the data as an argument. Again, we're going to reference the original raw data, EKG_DF, brackets, with quotes, ECG raw. That's the first argument. And then the window length, considering it's 1,000 data points, we could make the window length something like 10. We could say, hey, if I want to smooth this data point, consider its 5 neighbors to the left and right of that data point in the smoothing. If you consider all of the neighbors, like if I said, hey, make the window length 1,000, it would super duper smooth out all of the spikes and the R waves would basically disappear, and that would not be a good thing. It would be too smooth. So we need to pick a small but reasonable window length. So let's just use 10 for now. Window length equals 10. And we can also just write 10. There are some functions in Python where you have to say exactly what the argument name is, but just know that we can just write 10 for this one. And then the polynomial order, it could be something like 2 or 3 or 4, and this is a reference to the polynomial being squared or cubic. If you remember from math classes, a cubic polynomial can be a little bit more dynamic, have some sharper curves than just a square function. So let's, for now, let's try 3. We'll make it a cubic polynomial. So let's run this. Before we do, let's assign the output to, we'll say Savitzky-Golay filtered EKG with an equal sign. Let's run this. All right, that has run. Let's print the output and see what we got. And again, we have an array of what looks like similar but slightly altered data, thanks to the filter. And to plot this again, we can do the same plt.plot function. So let's write plt.plot, and as its argument, give it the Savitzky-Golay filtered EKG. And we'll run that cell and look at the output. And it looks pretty smooth. It's not bad. One thing we have to watch out for with filters is that if there are big sharp peaks, we want to keep those peaks because they're meaningful, especially in EKGs. The R wave, both its location and even its height, the exact voltage of the R wave, can tell us a lot about whether the heart is experiencing disease or not. So if we were to pick the wrong polynomial order, or we picked too small or too big of a window length, it would smooth out these sharp edges and the EKG would lose important information. And just to illustrate again, let's zoom in on just the first couple of heartbeats. So we'll reduce the data even further with indexing. We'll write Savitzky-Golay filtered EKG brackets. And from that data, let's just again choose the first 200 data points. We'll rerun that. And then look how smooth that is. The Savitzky-Golay filter actually did great. It preserves the sharpness of the R peaks and the Q and S waves. And we can also start to make out, okay, there's a P wave. Oh, and look, there's a T wave just to the right of the R wave. Looking back at the QRS complex again, we're supposed to have, in general, a big R wave, and then on the left and right, we have the P and T waves, these little bumps. And then immediately next to the R waves are these little dips, the Q and the S waves. So just think big spike, little to medium bumps on the left and right, and then little dips right next to the R waves. And that's pretty much what we're starting to see in our smooth EKG. We see a P wave, big R wave, a little bit of a T wave, and then we see the Q and the S dips to the left and the right of the R wave. So the Savitzky-Golay filter did great. When we talk about the polynomial that we're using to smooth with Savitzky-Golay, this is what we mean. You can see that the algorithm is moving a gray box along the noisy data along the line, using all of the neighbors of the data point that we want to smooth, and fitting a polynomial equation to that. And then whichever value is at the center of that fitted polynomial, that's the data point that gets saved. The polynomial shown in this particular animation has a degree of 4. You can also see at the top of the graph that the window length is 45. That means it's using the 45 neighbors of the central data point to make its calculation. The filter that we just showed you had a window length of 10, and we gave our filter a polynomial of 3. That's a cubic polynomial. The greater the polynomial, the more nuanced the curve can be, but if you go too high to like an order of 10, then the curve can be so nuanced that it accidentally includes too much noise in the result. So again, this was the output of the Savitzky-Golay filter on our EKG. Alright, the last of the 3 filters is going to be the Butterworth filter. This filter is going to be different from the median and Savitzky-Golay filters because it filters on frequency. The median and Savitzky-Golay filters used a data point's neighbors to determine what its smoothed value should be. However, the Butterworth filter doesn't consider any of that. It just works on frequencies. What does that mean to filter on a frequency? Well, when you have a signal, we can say this is a low frequency. It doesn't peak very often. Something like this will have a high frequency. It peaks frequently. Frequency filters allow us to pluck out certain frequencies or get rid of them from certain signals. If we were to have a signal that looked like this, it was a combined low frequency and a high frequency, We could use one of the frequency filters to say, hey, I only want the low frequency. You could put it through a frequency filter and then just get out the smooth signal. And then likewise, if you said, hey, I want to get rid of the low frequency and I just want the high frequency stuff, then the result would just look like this without the low meandering underlying signal. This is something that we can do with a Butterworth filter, and Butterworth filters are just one of many types of frequency filters. You can actually check out more frequency filters in the SciPy documentation. These are all the kinds of filters that SciPy makes easy to use in Python. So the goal for our Butterworth filter is for it to smooth out our EKG signal, but also preserve some of the spikiness. We want it to smooth things, but not too much. So as far as the code, this one's going to be a little bit more complicated than the last few, but not too complicated. We'll explain all of the arguments that you have to give to the Butterworth function, so that even if you're new to coding and signals filtering, it will still make sense. So to do a Butterworth filter, the main function we have to call is going to be scipy.signal.butter, parentheses. Now before we start this filter actually requires two steps. One is that we have to create the filter itself, and then we have to use a separate function to combine our data and the filter. In SciPy, the Butterworth filters are structured in a way that you create them, and then you can reuse them on a bunch of signals. So that just means we have to call the butter function, grab our saved generic filter that can be reused, and then combine it with our EKG data. So actually what we'll end up doing is running the butter function that's written out here, and then later we're going to use SciPy's SOS_filter function. And this stands for second order sections filter. And though that doesn't make sense right this second, think of it as a type of filter function that is going to easily accept the data in the particular format that the butter function is going to output. Alright, so let me change this SOS_filter so that Python can find it. It's actually scipy.signal.SOS_filter. Okay, let's give the butter function our actual parameters. We're not going to give it our EKG data just yet because we're just making the reusable filter itself. So here are the arguments that we have to give it. And remember, arguments is the same word as parameters. We're just giving the function stuff to make decisions with. So we're going to give it 5 arguments. And you can see what the arguments are and little explanations about them on the scipy.signal.butter documentation page. The link will be in the description below. The first one we have to give is the order of the filter. Just like with Savitzky-Golay, we're going to kind of tell it how intensely to filter. When it comes to frequency filters, ideally we would be able to say, if we're just looking at a signal, this is high frequency on the right, low frequency on the left, we want to be able to say, okay, I only want these frequencies and I want it to stop at exactly, 500 hertz or something, or I only want everything exactly higher than 650 hertz and the like. Math does not work that way. Because of mankind's limitations in the understanding of math, filters actually have to have a bit of a drop-off. You can't say, okay, I want only exactly all the frequencies lower than a certain number of hertz, and then just have the filter get rid of exactly everything at that point. There needs to be a bit of a slope. Some signals to the left or the right of your cutoff will accidentally still make it into the resulting signal. They'll be quieter, they'll look like they're kind of gone to the human eye, but they'll still technically be there. So when we're determining an order of our filter, we're telling the filter how steep we want this drop-off to be. This not so steep line, A, on the top, has a lower order than, say, line E at the bottom. E has a steeper drop-off. So as far as knowing what order we want to use for our EKGs, it's going to be a little bit of a guessing game. We're going to use a number like 3 or 4 or 5. So in the comments, I'm just going to write, as I write out all the arguments, I'm going to say filter order. We're just going to note to ourselves in this code comment. Remember that comments don't run. You can just put notes to yourself, put a little # or hashtag symbol, and then write whatever you want to yourself just to remember stuff. So I'm going to write filter order equals 3. I'll remember to put that in the parentheses in the arguments later. The second argument is the cutoff frequency, specifically known as the critical frequency. Now we know that we want to get rid of super high frequencies. That's what the noise in our original signal is. It's just a bunch of jagged stuff. That's high frequency. So this will be a little bit of a guessing game, but let's start with 15 hertz. I'm going to say we want to keep everything in our signal that is less frequent, a lower frequency than 15 hertz, and that should get rid of most of the noise while preserving the spiky R wave peaks. So we'll remember to give 15 as an argument to the butter function in a second. The third argument, and again I'm going to the SciPy butter functions documentation page, which is linked in the description, to know what these arguments are supposed to be. This third argument tells the function what type of filter do we want to do. Do we want to do a low pass, high pass, band pass, or band stop? What that means is the type of filter is saying what frequencies do we want to go through. A low pass filter lets low frequencies pass through. It keeps the low frequencies. A high pass filter lets only the high frequencies through. So for ours, if we want to get rid of high frequencies, we'll do a low pass filter. We'll just keep the low frequencies. And on that note, there's also band pass and band stop. That's basically what this is. It says, hey, I want to keep low frequencies and some high frequencies, but I want to get rid of a chunk in the middle. That's a band stop filter. And then the opposite is band pass. I just want to let a chunk of middle frequencies through, and I want to keep those. So the butter function, we will tell it we want to do a low pass filter. All right, the fourth of 5 arguments, we have to tell it the sample rate of our signal. Because how does it know? It doesn't know whether we took 1,000 samples per second for our EKG or 360 samples or whatever. That affects what frequency it thinks a signal is and then what the filter ends up filtering out. So we know from our data set, from the metadata JSON file that corresponds with this EKG, again, we can go over here to the right to the data tab, click the actual file, and it will pop up in a window at the bottom of the Kaggle page. We sampled, or MIT sampled this data at 128 hertz, 128 samples per second. So we're going to tell our filter that that's what the frequency rate was. And then the last argument just tells the butter function what we want the output to be formatted as. We're going to set this to SOS, which stands for second order sections. If you want to learn more about that, come over to the butter functions documentation page. There are a couple options for what you want the output format to be. And then the output format affects what kind of final filtering function you actually use to combine the filter with your data. That's why down here we use the SOS filter function. Alright, so we just wrote a bunch of comments. We didn't actually give the butter function anything. So to make our actual filter, let's give it the arguments. The filter order is the first argument. We'll write 3. The frequency that we want it to cut off at is 15. And then we'll say, as a string with either single quotes or double quotes, either works, we'll say we want to do a low pass filter. If we wanted to do a high pass, we just write high pass. If we wanted to do a band pass or band stop, you can write those, but we'll write low pass. All right, comma, space, the sample rate. Now the literal name in the code for this argument is fs for sampling frequency, so we'll just write fs equals. And for any folks who are new to Python, there are some arguments where you can give them implicitly. You don't need to name them when you write the function, but then optional arguments, you may need to write them out explicitly. Because if things are optional and they're missing, then Python's like, oh, I don't know what you mean. You put a 4th argument in this function. Did you want that to be the output or the frequency? What are you doing? So for optional arguments, you have to be explicit. So we're going to write frequency equals 128. And then our last argument, also an optional argument, so we have to be explicit. We'll write output equals quotes SOS. And that says we want the output to be in second order sections format so that we can feed it into an SOS filter function. Again, that's not the only way to do it. There are other output formats, but this is what we're going to do for today. All right, so there's the code for our filter. In order to save it, let's assign it to a variable called butterfilter. So write butterfilter equals the function with all of its arguments. Let's move the SOS filt. I just cut that out. We'll move it to its own block that will run in a second. All right, let's create the butter filter. We'll run this block of code. And now our butter filter exists. So now all we have to do is run this filter and our EKG data into SOS filt. That means all we have to do is write butter filter and then our EKG data. We'll get that same chunk of raw EKG data from before. It's this one, this 1,000 data point long raw EKG. Let's rename this. Raw EKG equals those 1,000 data points just for readability. We don't have to do this line. So SciPy.signal.SOSFilt, and then the arguments are the butter filter and then the raw EKG. And then to save this, let's call it filtered EKG. And let's run that. All right, let's take a look at what the output was. Should be just a bunch of voltages. All right, we have an array of 1001 data points. Let's plot this with plt.plot and see what we got. All right, and there is our smoothed EKG. Let's do what we did before, where we zoom in on just 200 data points. Filtered EKG brackets 0:200. Let's rerun that. And look how smooth that signal is, and it preserved the R waves. That's pretty good. That looks even smoother than the Savitzky-Golay one. Now, you don't necessarily want everything to be exactly smooth. Sometimes doctors and paramedics and nurses want these little jagged edges, especially around the waves. That can tell them a lot about the heart. And if we thought the Butterworth filter filtered out too much, we could change the frequency that it filters out. We could set this to 20 Hz and see how that fares. Let's rerun this actually. We'll try with a cutoff frequency of 20, rerun the raw EKG cell, rerun the filtered EKG cell, and then we'll replot. Let's see how that looks. Okay, a little sharper around the edges. That seems to preserve the signal in a good way without adding back too much noise. So those were all 4 filters. We did the Neurokit default filter, we did a median filter, a Savitzky-Golay filter, and then a Butterworth filter. As a reminder, we started with the raw EKG data, and then we ran it through Neurokit. This is what the data looked like when we started. Here's 13 heartbeats of raw EKG. Zooming in, here's how noisy it was. Here was the output from Neurokit's ECG process function. Here was the result from a median filter. Didn't do as well, but it did okay. Still some jagged edges that are most likely just noise. Here was the Savitzky-Golay filter. And then here was the output of the Butterworth filter. So those are a few methods to smooth out EKGs. Those aren't the only methods, but those are some pretty easy ones to start with in Python. Remember, there's Neurokit, which does extensive EKG processing all in one go. And then there are the median and Savitzky-Golay filters, which use a data point's neighbors to filter. And then there's Butterworth, which is a type of frequency filter that gets rid of or keeps data based on its frequency. That's all for today. The dataset that we used here and this Python notebook that you're looking at right now will be linked in the description. They are on Kaggle, they're free. I would recommend making a Kaggle account and getting started with coding as soon as you can. If you have any feedback or questions, please leave them in the comments. Thanks for watching.